okay? So if you didn't do it by that method, you didn't show the understanding I was looking for. So any other questions about the quest? No? Okay, so you guys did well. So let me give you a handout. This is going to be a handout for 6.6. I might as well give it to you right now. Okay, so everybody should have the scatter diagram handout. So this is just about how to do scatter plot on the TI-83 or 84. So this is something you would have already done in 111 at least a little bit, or if you took 243, you would have done it in that class too. So let's go ahead and I want to just clarify something from last class because I kind of botched the example that we did a little bit. Because I mixed up some numbers. So the last example that we did yesterday, I stated it as, just to clarify, so correction to example from Tuesday. So this was from section 6.4. So it was supposed to be 6.4, number 50 was the problem. And the question was to graph y equals 4 sine of pi over 2x minus 2. What I did was when I was looking at the amplitude factor, and this was, I did it in my notes too, so I feel silly. But when I was looking at the amplitude factor, for some reason I looked at the A from the previous example that we had done, and the A there was 4/3. So I carried the 4/3 through the problem. So if you just change the 4 here to a 4/3, that'll fix everything for the example. Okay, so just proceed as if it were 4/3, as if A were 4/3. So replace the 4 with the 4/3 and everything will be fine. Okay? So does that make sense? You know, you'd have to have been here Tuesday for it to make much sense, but hopefully it makes more sense now if you were here Tuesday. If that were confusing, the reason is because of this. Okay. So, all right, so let's go ahead and get started. Are there any homework questions? Quest, oh, the handout? Did you get your quest also? Okay, so who else has not gotten the quest or the handout? Just you? Okay, and your name?
Jason.
Jason Height? Here's your quest. The handout. Okay. So section 6.5, let's get to that if there are no 6.4 questions. Shall we? Okay, so 6.5 is about the graphs of the other 4 trig functions and transformations of those. So we considered the graphs of sinusoidal, certain sinusoidal functions in 6.4 of the form y equals a sine of omega x plus b, or y equals a cosine of omega x plus b. So now we're going to consider the other 4 trig functions of that form, y equals a tangent omega x plus b, cotangent, cosecant, secant, etc. So what I'm going to do in this section, I want to go through it pretty quickly, so I'm just going to touch on some things. So I'm going to discuss primarily the graphs of the tangent function and the cosecant function. The cotangent and secant functions are going to be similar respectively to the tangent and cosecant functions. So basically whatever we did in the case of tangent and cosecant, just take those similar core graphs for cotangent and cosecant and apply the same basic principles of transformations, period, that kind of thing, okay? The period of cotangent is the same as the period of tangent, the period of cosecant is the same as the period of secant. So let's start with tangent. Section 6.5, graphs, tangent, cotangent, secant, cosecant functions. So our emphasis is going to be on the tangent and cosecant. And the others will be fairly similar. Okay, so let's start with the tangent. Okay, so graph y equals the tangent of x, where x is in radians. So from here henceforth, unless otherwise stated, the angles are going to be in radians always. Okay, so to get a graph of the tangent function, it may help to begin with a graph of the sine and cosine functions simultaneously on the same coordinate grid. So let's start with those and then see from our understanding of the quotient identity, tangent of x equals sine of x over cosine of x, see if we can determine what the graph of the tangent function would look like. Okay, so begin by graphing. I'll use multicolors here. Y equals sine of x, and y equals cosine of x in the same coordinate grid, in the same coordinate system. Okay, and then we'll see, okay, how are the asymptotes, there will be vertical asymptotes for your graph of your tangent function, how are those related to certain key points on the cosine or sine function, and so on. All right, so let's do those. Okay, so I have my coordinate axes scaled. So the horizontal axis is scaled by increments of pi over 2, pi over 2, pi, 3 pi over 2, and so on. And the vertical is scaled by increments of 1. So graphing the sine function first. So you could just do our 5 key points and get the graph very quickly. So sine function, I have a midline point at the origin. I have a max at pi over 2. I have a midline point at pi, or a 0. I have a min at, and in fact, why don't I just dash in the lines y equals 1 and y equals negative 1 to help construct these graphs. So just dash those in. Y equals 1. Okay, so constructing the graph of sine x, y equals sine of x. 0, 0 is on the graph. Pi over 2, 1 is our max. Pi 0 is another midline point. Then I have 3 pi over 2, negative 1 is a min. 2 pi 0 is a midline point. So I have one full period between these 5 points, and I can just fill that in with smooth curves. Okay, so each midline point is going to be what's called an inflection point, where the curvature changes from concave downwards to concave upwards. So each midline point on your sine or cosine graph must be an inflection point. Okay, and those are going to be the only inflection points. So I have an inflection point at pi, and then a min at 3 pi over 2, another inflection point at 2 pi, etc. And going to the left, I had a midline, so I'm going to go down to a min, and then another inflection point, and then a max, and a midline, and so on. Okay. So there's my sine function. And let's graph the cosine function on the same coordinate system. So the cosine function, the period's also 2 pi, except the wave has been shifted over pi over 2 units to the left. The sine wave would be shifted over pi over 2 units to the left. So I'm going to have a maximum at 0, 1, then a midline at pi over 2, 0, then a minimum at x equals pi, then a midline at 3 pi over 2, a max at 2 pi. And the points are just going to alternate like that. Max, midline, min, midline, max, midline, min, etc. Okay, so midline, min, midline, max. So then I'm going to connect those points with smooth curves. So maximum, inflection point, minimum, inflection point, maximum, and so on. Inflection point, minimum, inflection point, maximum. Okay, so we have y equals cosine of x. All right, now tangent of x is the sine of x over the cosine of x. So y equals the tangent of x is the sine of x over the cosine of x. So that means that when the cosine of x equals 0, we're going to have a vertical asymptote for our tangent function, right? The tangent would be undefined. So I have something that approaches 1 in the numerator, or negative 1, and 0 in the denominator. I'm going to get a vertical asymptote as a feature every time I have an x-intercept for the cosine function. So if I just look at my cosine function graph, see where all those x-intercepts are, those midline points? I'm going to sketch in vertical asymptotes there, okay? Because that's where my denominator is going to equal 0. Does everybody understand that? Okay. So let's sketch in some vertical asymptotes. everywhere we see an x-intercept of the cosine function. So that's going to be minus pi, 0, pi, 2 pi, etc. Just dash those in. Minus pi, 0, pi, draw one more vertical asymptote at, wait a minute. I'm sorry, I have this wrong. The zeros of the cosine function are going to be, okay, so this is minus 3 pi over 2. This one's right. The second one I got wrong. So minus pi over 2 is going to be when I have another 0 of my cosine function, okay? So cosine of minus pi over 2 is going to be 0. That's on the negative y-axis, so the x-coordinate is going to be 0 when x equals minus pi over 2. So let's sketch this one in. Apologize for that. Okay, so this first leftmost asymptote is x equals negative 3 pi over 2. We have x equals negative pi over 2. And then I have another one. I'm going to erase this one because this doesn't correspond with an x-intercept of the cosine function. So this one is going to go away. So this vertical asymptote should have been at pi over 2, not at pi. Okay. Sketch another one at pi over 2. So I'm just going to construct the graph, and once it's been constructed by this process, we don't have to repeat the process every time we want to draw the graph of the tangent function. We could just remember its important features and then just draw it based on that. So this is to develop the graph of the tangent function. So I have x equals pi over 2, and then 3 pi over 2, I have another x-intercept for my cosine function, so I'm going to sketch that asymptote. So next, since the tangent of x equals the sine of x over the cosine of x, one thing that's true is that when the sine and cosine of x are equal to each other, the ratio is going to be equal to 1, right? So I know at what x the tangent function is going to equal 1, okay? So pi over 4, for example, the sine and cosine are equal to each other, right? They're both equal to root 2 over 2. Sine of pi over 4 and cosine of pi over 4 are the same value of root 2 over 2. So when I form the tangent of pi over 4, I'm going to get 1, right? When I have equal numerator and denominator, the ratio is 1. So whenever I see points that have equal sine and cosine, the value of my tangent is going to equal 1, okay? So here, the sine and cosine, this is right at pi over 4, they're going to have equal value. So I'm going to put a point for the tangent graph of pi over 4, 1. Okay? Similarly, when they're both negative and equal, that's going to be, for example, 5 pi over 4. The tangent of 5 pi over 4 is also equal to 1, because the sine and cosine of 5 pi over 4 is going to be negative root 2 over 2 for each of those. So when I take negative root 2 over 2 divided by itself, I'm going to get 1. So that means at this point here, the sine and cosine are also both equal. So I'm going to get another tangent value equal to 1. And then I'll just continue doing that. Wherever I see the sine and cosine equal, I'm going to put a point at y equals 1. Okay? So those occur. The tangent function equals 1 basically at pi over 4, 5 pi over 4, negative 3 pi over 4, etc. Okay?
So they appear to intersect with those two, with the sine and the cosine intersect, whether in the negative or the positive?
Right, because when they have this, when they intersect, they're going to have the same function value, right? So when the sine and cosine have the same function value, the ratio of equal numbers is always 1, unless those numbers are 0. So, but neither of these points satisfy y equals 0, right? So the ratio is always going to be 1. So I'm just going to put wherever sine equals cosine, for that value, I'm going to put 1 for my tangent, because sine over cosine will be 1, okay? So, and also when sine and cosine have opposite values, my tangent is going to be negative 1, okay? So let's see, where would the sine function equal root 2 over 2 and the cosine function equal negative root 2 over 2? What theta would you have, for example? 3 pi over 4 would be one such theta. So if I go to 3 pi over 4, let's see, so 3 pi over 4 is right here. So we have opposite values of sine and cosine. So I'm going to put a point at negative 1 for the tangent there, okay? And then similarly, wherever I have opposites, I'm going to put a point y equals negative 1, okay? And then I have another pair of opposites, it looks like here. So y equals negative 1, and so on, okay? Now, let's think a little more through this. When the sine is greater than the cosine, let's say both of them are positive, the ratio is going to be greater than 1, right? If I have a greater numerator than the denominator, say 2 over 1, that ratio is going to be greater than 1. So wherever my sine and cosine are both positive, but the red curve is higher than the blue curve, my tangent function values are going to be greater than 1. So that's going to be all this interval between here and here. You see the red function is higher than the blue curve. So I'm just going to have my ratio is going to go above the line y equals 1. And so as this cosine approaches 0 and the sine approaches 1, the ratio is going to approach infinity. So I'm going to get my asymptotic behavior there. This isn't quite vertical, but it'll become very, very steep, okay? And then, and it's not going to be an inflection point or anything. When the ratio is less than 1, so when they're both positive and the cosine is greater than the sine, so I would have, say, 1 over 2, the denominator is greater than the numerator. I'm going to have a value that's positive but less than 1. So I'm going to be below 1 but still positive through here, okay, wherever my blue curve is above my red curve. And then I'm going to continue in that fashion for the rest of the graph. So there's this. And then let's see. The cosine function is positive and the sine function is negative, but the sine function is smaller in absolute value. So I'm going to have between negative 1 and 1 here. So a little inflection point here. And then here my sine function is approaching negative 1. My cosine function is positive and approaching 0. So the ratio is going to approach negative infinity. So there's my asymptote. And then that pattern is just going to keep repeating. We'll get this same shape. It looks kind of like this. You know, here are asymptotes. It's going to look kind of like this-ish. We'll get that same shape repeating periodically infinitely often to the left and to the right between my asymptotes. So I'm going to have another, so I know my sine is 0. For example, if wherever my sine function equals 0 and my cosine doesn't equal 0, I'm going to have an x-intercept for my tangent function, because sine over cosine, 0 over 1, for example, would equal 0. So wherever I see intercepts of the sine function, I'm also going to have intercepts of my tangent function, x-intercepts, okay? So I'm going to have those at pi, at 2 pi, etc., minus pi, minus 2 pi are going to be intercepts, x-intercepts of my tangent function. So I'll just continue in this fashion and construct my curve. Another inflection point. Each x-intercept is also going to be an inflection point. It doesn't look real inflection pointy the way I've drawn it because it's kind of stretched out looking. But anyway, it's just going to continue like this. Okay. that point to that point. Okay, etc. So it's hard to discern the graph with all that clutter on the page there. So I'm going to give you an image of the graph that's a little bit decluttered. So the purpose of having the sine and cosine on there was to help us construct the graph, analyze and how to construct the graph. Now that we know the general shape of it, we can just memorize that shape. So here it is. So you see several periods graphed at the bottom of page 414 here. Okay? And you see that the tangent function is going to equal 1 at pi over 4, 5 pi over 4, 9 pi over 4, etc. It's going to equal negative 1 at minus pi over 4, 3 pi over 4, etc. Okay? So I can remove all that clutter. That's basically going to be what the graph of my tangent function looks like. So I won't draw that again by hand, but you see, everybody see how it basically looks, okay? And does everybody understand why it looks like that? The vertical asymptotes are because the cosine equals 0 at those points, so you're going to have an undefined function value there. So you'll get vertical asymptotes at that point. The x-intercepts occur when the sine function equals 0. The numerator is 0 and the denominator is not 0, so we know the function value has to be 0 at these multiples of pi, and so on. So on any given period, the tangent function is strictly increasing on any given period. You see that? Okay. So I'll just write out some characteristics of the tangent function, or its graph. So we have our x-intercepts. Where would our x-intercepts occur? Integer multiples of pi, right? Do you see every x-intercept is going to be at an integer multiple of pi? That is to say, the x-intercepts will occur when the sine of x equals 0. That happens at integer multiples of pi, okay? So I'm going to say x equals k pi, where k is an integer. Okay? So the vertical asymptotes. So by the way, I'll point out that the x-intercepts correspond with those of the sine function. Same as those of y equals sine x. So the vertical asymptotes are going to correspond with the zeros of the cosine function. So that's going to be an odd multiples of pi over 2. So I'm going to have x equals 2k plus 1 times pi over 2, where k is an integer. And these correspond with the x-intercepts of the cosine function, or the zeros of the cosine function. Since the cosine function's in the denominator, when you get a 0 in the denominator, you're going to end up with a vertical asymptote in this case, okay? What else do we have? The period of the tangent function. What's the period of the tangent function? Anyone remember?
Pi.
Is pi, right. You can see that the pattern of the graph repeats every pi units. So for example, we can count where our asymptotes fall. Minus pi over 2, pi over 2, 3 pi over 2, etc. The distance between successive vertical asymptotes is pi. So that's the length of our period. And then what type of function is tangent? Odd, even, or neither? Hint, look at the graph. What kind of symmetry does the graph have?
Sine.
It has rotational symmetry with respect to the origin. Odd functions have that kind of symmetry, okay? And any function whose graph has that symmetry must be odd. We've already established that the tangent function is odd because the sine function's odd and the cosine's even, thus the ratio is going to be odd. So tangent is odd. So I could say that the tangent of minus x equals minus the tangent of x, okay? And that's about it. So let's say that we have a transformed tangent function. So let's say we do a vertical stretch or compression, maybe a reflection over the horizontal axis and a horizontal stretch or compression. So how would that affect things? So y equals a tangent of omega x plus b. So A is a vertical stretch or compression factor. If A is greater than 0, and you're going to get a reflection. In addition to that, you're going to get a reflection over the x-axis if A is less than 0. So in addition, reflection over x-axis if A is less than 0. So the absolute value of A in that case would determine the amount of stretching or compressing vertically that you'd have. Okay? So the omega is your periodicity factor. So if I have a function of the form y equals a tangent of omega x plus b, then the period, remember with the sinusoidal function, if it were a cosine or sine of omega x plus b, the period would be 2 pi over the absolute value of omega. 2 pi being the period of an untransformed sine or cosine. So tangent, the period of a non-transformed tangent function is pi. So to get the period of this transformed function, I'm going to divide my pi by the absolute value of omega instead of 2 pi. So it'll be t equals 2 pi over the absolute value of omega. If omega is positive, of course, you wouldn't need the absolute, excuse me, t equals pi. I just got done saying that. T equals pi over the absolute value of omega. So if omega is positive, the absolute value is unnecessary, and we could always rewrite the function definition such that omega is positive by using the odd property. We can bring the minus sign outside of the argument of the function. Okay. So if we had y equals tangent of minus 2x, I could write that as y equals minus tangent of 2x, and then in that case omega would be positive 2. Okay. So, but this is sort of a general setting. If you don't use that even or odd property and leave omega as is, then you would have to take absolute value. Okay? So, let's go ahead and try an example. Keep it simple here. By the way, on your graphing calculator, you could get a nice graph of the tangent function. So I'll just show you that on the calculator. Be sure that it's set to radian mode. So mode. Radian, my calculator's already in radian mode. Go to my y equals and graph tangent of x. And I'm going to select a trig window by going to my zoom key. So this will automatically fit my window to a convenient setting. Zoom Z trig. And there we see several branches of the tangent function there. And since my calculator is not ancient, it doesn't try to cross over asymptotes with the curve. Some of those older TI-83s, it'll actually try to connect across a vertical asymptote. And I've seen people back in the day, you know, draw the graph as if it looks like this, you know, and that shows to me, you know, most of you probably don't have a calculator that old, but that would telegraph to me you know nothing about asymptotes. So don't do that, just going off of what the calculator.
So you hit the Y button?
Huh?
You went the mode to get the radian, and then you hit the Y?
And then I went to Y equals, entered tangent of X, so the tangent key is down in your 4th row of buttons there.
I was just wondering why it wouldn't go to Y. Okay, just
So Y equals.
Y equals. It
And
says
then,
R1. So forth.
oh, you must be, oh, you're in polar mode.
Oh,
So I'm going to change your, I'm going to change your mode to function. Okay. We'll do polar mode later in the term.
Okay.
So now go to Y equals, and then you could go ahead and enter your tangent of X.
Great. Okay.
Okay.
Great. Thank you.
And then select zoom 7 for the trig setting, trig window setting. Okay. So let's do this example. So sketch graph of y equals tangent of pi over 2x. Okay. So we have a equals 1, so there's no stretching or reflection, right? And when I say no stretching or reflection, I mean of the graph of tangent of x, y equals tangent of x. So that's our core graph. And we have omega is what? Pi over 2, that's the coefficient of x inside the argument here. So omega is pi over 2. And b is 0, so we have no vertical shift. So the b in the formula would give you any vertical shift, okay? Just as always, with any function. So let's go ahead, since omega is equal to pi over 2, let's find the period of this function. So omega equals pi over 2, that implies that t equals pi over omega, or pi over the absolute value of omega, pi over 2 is going to be 2, okay? So this tangent function has a period of 2. So all we've done is horizontally stretch the tangent function, the original tangent of x function, y equals tangent of x. So moving on. So where the tangent function has vertical asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, this one's going to have vertical asymptotes at 1, 2, 3, and so on. Okay. Okay, so you found that the period is 2. So with our tangent function, let's just take a quick look at our graph here. Our tangent function with period of pi, an amount equal to a period separates successive x-intercepts. Do you see that? So every successive x-intercepts, the distance between them equals pi. Okay, so since the period of this one is 2, my successive x-intercepts are going to be separated by a distance of 2. Does everybody understand that? In this case, it was separated by a distance of 1 period, which is pi. With our function, the period is 2, so we'll just replace the pi's with 2's in our graph here. So I'm going to have an x-intercept at the origin, another x-intercept at 2, another x-intercept at 4, another one at -2, and another one at -4. Okay?
Is that where the vertical asymptotes go?
This is where the x-intercepts are. Okay, so my x-intercepts would have been at 0, pi, and 2 pi, etc. for the tangent function, but instead of my period being pi, it's going to be 2. So they're going to be, instead of 0, 1 pi, 2 pi, and so on, it's going to be 0, 2, 4, etc. So the distance between successive x-intercepts is equal to a period. My sort of reference x-intercept is at the origin, okay? So I just go by the distance of a period to get all of my x-intercepts there between x-intercept points. So then my vertical asymptotes, the distance between them is also 1 period, and they occur every half period. So pi over 2, 3 pi over 2, etc. So a half period is going to be 1. So I think I misspoke earlier about the vertical asymptotes. They're going to be at -1, 1, 3, 5, -3, and so on. So they're going to be at odd integers, okay? So I'm going to have vertical asymptotes at odd integers. So I'll just pencil those in, those dashed lines. So do your sort of basic features first, your x-intercepts and your asymptotes, and then let those features guide your rest of your graph, okay? So all those asymptotes, they're not actually on the graph itself, they just are features that help determine the shape of the graph. So now, I'm just going to get some points here. So remember, at pi over 4, or a quarter period, I had a function value of 1, right? So a quarter period here, the period's 2, a quarter period is going to be at 1/2. I'm going to get the point 1/2, 1 on my graph. So I'll just plot that. So 1/2, 1 is going to be right there. I'm also going to have -1/2, -1. Okay. So I'm going to draw my curve. I have an inflection point at the origin, and then asymptotic behavior away from the origin. Inflection point. So the graph is actually concave down on the left side of an intercept between the left side of the intercept and the vertical asymptote, and concave up between the right side of the intercept and the vertical asymptote. So concave down looks like this, concave up looks like that. Okay, so you can see it's sort of cupping upwards to the right of my intercept and sort of concaving or cupping downwards to the left of it. Okay? You'll study those concepts more in depth in calculus when you take calculus, if you take calculus. So we'll just do the same thing and just repeat this same pattern each period. So I'm going to have my x-intercept, then I know a quarter period beyond 2. I'm going to have a function value of 1. A quarter period to the left of 2, I'm going to have a function value of -1. And so construct from there. Inflection point at 2 and an x-intercept, etc. And just draw maybe 2 or 3 periods. So a quarter period to the right of -2, I have a function value of 1. A quarter period to the left of -2, I have a function value of -1. And then I can fill in the remaining behavior. Just draw it sort of in a piecewise fashion like this. Etc. So then I'm going to have the same deal here. So there it is. And I can continue if I wish. So this is so we have y equals the tangent of pi over 2x. Okay? Make sense? All right. So basically, all I did was I adjusted my period accordingly. If I have a reflection or a stretch, I have to take that into account. So with a stretch, if my coefficient a was equal to 2, I would multiply all of my function values by 2. So where I was plotting function values of 1, instead they would equal 2 if I had a 2 for my coefficient. If I had a 1/2, those 1s would then become 1/2s. Okay, so that will help you with your vertical stretch or compression. And then the vertical shift, if you draw the unshifted curve and then bump everything up or down by the amount equal to the vertical shift, then that's easy to get as well, I hope. All right? So any questions about that? We can check our answer on the calculator if you want.
So when you stretch it at the 1/8 of an interval, is that where it should cross that line? So if that was 3 tangent, at the 1/8 of an interval, it should cross the 3?
So basically, it's going to be a quarter period to the right of an intercept or to the left of an intercept is where you're going to get 1 or -1 for function values. So if you're at an x-intercept, if you go a quarter period to the right, you're going to get a function value of -1. So the period is 2, a quarter period is a 1/2. You see where that is?
So that would be, if that was 3 tangent, that would cross at the 3?
Exactly. So if this were 3 tangent of pi over 2x, then I would have this point being a 3, a y equals 3 instead of a y equals 1. Okay? Does that answer your question?
Yes.
Good. So moving along, you're going to check on the graphing calculator. So I will enter my equation, y equals the tangent of pi over 2. I'll just call it pi x over 2. Same thing. And then graph it. And since I chose a trig window, that doesn't work so well because my periods are multiples of 2 instead of multiples of pi. So I'm going to get, let me just change this to a standard viewing window. So zoom 6, and then maybe that's too much detail, too much of a scale. So let's go back, and I'm going to change my x-min to say, just to fit what I have there, -4 to 4, let's say -4.5 to 4.5, and my x max, y min will go say -5, y max 5. Let's try that. So that's going to look a lot more like, you can clearly see that's what we have for our graph, right? Okay. Any questions? Yes, Michelle?
In the last viewing window, why did it have some of them cut off?
Oh, because there's not enough resolution to get the curve. You know, they have to, the graphing calculator, what it does is it highlights a pixel if there's a point in that pixel that corresponds to a function value, a point on the graph. So pixels aren't infinitely small points. They take up some space on the screen. So if there's not enough screen space for a full pixel, it's just not going to fill in that pixel. Okay. If you have a really high-res calculator, some of the newer ones have like the LED displays, you won't get that happening as much, okay, because it's much higher resolution. So this is pretty low res, that's why it's doing that.
In the y, did you have the tan with the pi over 2?
Yes, so my y equals, it was the tangent of pi x over 2.
Oh, pi x over 2.
Yeah, because you need a variable. So moving right along, any questions then about the tangent function? Feeling good? All right, so moving on to the cosecant function. to construct the graph of the cosecant function in a similar way that I did with the tangent function, except it'll be a little less cluttery because I will only have to draw the sine function instead of both sine and cosine as a reference there, okay? So the sine function is going to determine my vertical asymptotes of my cosecant function as well as my maximums and minimums, okay? So let's do y equals cosecant of x. So I'm going to start by drawing the graph of y equals sine of x. Since the cosecant is just the reciprocal of the sine function will help us determine a lot of important features of the graph of the cosecant function. So that's since cosecant of x equals the 1 over the sine of x. Okay. So let's do the graph of sine of x, y equals sine of x. So while I'm getting my coordinate axes set up, why don't you just as practice go ahead and graph your sine function, okay? So that we can be ready. So then I have, let's say this is pi, this is 2 pi, minus pi, this is 2 pi. Okay? So in addition, I'm going to pencil in the lines y equals 1 and y equals -1 for reference, because those will determine the mins and maxes of our sine function, as well as the mins and maxes of our cosecant function. Y equals 1. Okay, so sine function. Just quickly get it doing our 5 key points. Let's get a couple periods in here. So y equals sine of x, we'll do in red as before. So let's see here. I have x-intercepts at 0, pi, 2 pi, etc., minus pi, minus 2 pi. And then I have a max at pi over 2, a min at 3 pi over 2, a max at minus pi over 2, a min at minus 3 pi over 2. Yep. Okay. So then I'm going to go ahead and connect my key points with a smooth curve. So the sine function, sort of a wave, is going to start, if you will, at the origin. I'm going to go up at max, inflection point. And then inflection point, etc. Oops, wait a second. All right. This should have been a min, I'm sorry. So minus pi over 2 is a min, not a max. So that looks like it. So this 3 pi over 2, minus 3 pi over 2 is going to be a max. There we go. Okay, so y equals the sine of x. Everybody got that? And so let's consider what features the cosecant function would have, which is the reciprocal of the sine function. So remember the reciprocal function handout that I gave to you a few class periods ago? See if I can dig it out here. Seem to have a copy immediately handy. But one thing that, if you recall from that sheet, or just basic knowledge of math, so I have cosecant of x, y equals the cosecant of x, is 1 over the sine of x. So the cosecant is going to be undefined at what points? 0, pi, 2 pi, minus 2 pi, etc. So integer multiples of pi is going to be where cosecant is undefined. We will have vertical asymptotes wherever the sine function equals 0. So all the x-intercepts of our sine function will be vertical asymptotes of our cosecant function. Does that make sense? So pencil in those vertical asymptotes. One. Another. X equals pi. X equals 2 pi. X equals minus pi. And of course, x equals 0 is going to be another one. So every integer multiple of pi, I'm going to have a vertical asymptote. So let's think of in terms of your knowledge of reciprocals, okay? So one thing about reciprocals is that when a function is 0, its reciprocal is going to be undefined. So oftentimes that will lead to a vertical asymptote. Okay, so that's the case with cosecant. When a function equals 1, what's the reciprocal of that function going to be at that point? What's the reciprocal of that? Is 1. Okay, so wherever I have a sine function value equal to 1, that's where also my cosecant function will equal to 1. So the reciprocal of 1 is 1, so I'm going to have a point here for my cosecant, a point here at y equals 1 for my cosecant. And similarly, whenever the sine function is -1, its reciprocal, or the cosecant of that value, is also going to be -1, right? The reciprocal of -1 is -1. So I'm going to put -1s for cosecant values wherever my sine function also equals -1. Okay? So at this point, -2 pi 1, excuse me, -3 pi over 2, 1, negative pi over 2, -1. Those points are all shared between the cosecant function and the sine function. Okay? So next, let's think about this. If a number is positive and greater, well, if the number is greater than 1, what is true of, if a number is positive and less than 1, what must be true of its reciprocal? So let's say 1/2 is such a number. The reciprocal of 1/2 is 2, which is greater than 1, right? So any number that's positive but less than 1, its reciprocal is going to be greater than 1, right? So you see wherever the sine function is positive and less than 1, that's basically everywhere except at your maxes, right? So, below the horizontal axis. So basically all through here, between these two asymptotes, my cosecant function is going to be greater than 1. And in addition to that, as the sine function approaches 0, my ratio is going to approach 1/0, which is going to approach infinity, okay? So what I'm going to have is, let's say that the sine function is 1/2 at this point. The secant function is going to be the reciprocal of that, or 2, right? The sine function is 1/2 at this point. The secant is going to be the reciprocal of that, which is 2. The sine function is, say, 1/3 here. The secant function is going to be 3, etc. Sine function is 1/3. The secant function is going to be 3. So I'm going to get sort of this U-shaped piece between x equals 0 and x equals pi. So that's going to look kind of like this. So a lot of students say that that's a parabola, but it's not a parabola. Why is that not a parabola? Do parabolas have vertical asymptotes? No. Does this curve have vertical asymptotes? Yes. Thus it's not a parabola. It looks U-shaped, but not everything that's U-shaped is a parabola. So I have this U-shape facing upwards between 0 and pi, x equals 0 of pi. That's going to be the same situation between -2 pi and -pi, right? I have essentially the same behavior with my arch of the sine curve on that segment as I do here. So I'm going to get the exact same graph in this interval. Okay? And then I'm going to have the mirror images of those in these two other intervals. Okay? So for example, when my sine function value is -1/2, say at that point, my cosecant is going to equal -2, right? Right there. And when my sine function here is -1/2, my cosecant is going to be -2. When my sine function is -1/3, my cosecant is going to be -3, et cetera, et cetera. So I'm going to then have some points and I can connect them and I'm going to have a shape like this. So it's going to be sort of the mirror image of these other U shapes. Okay? So I'm going to have this region is identical to this one over here in terms of how the graph is going to be created. So I'm just going to make another such U shape between pi and 2 pi. Okay?
And this is the cosecant.
This is cosecant. Okay, so y equals cosecant of x. So it's going to alternate upward facing U shape, downward facing U shape, upward facing U shape, downward facing U shape. And none of those U shapes will ever intersect each other. Okay? And they can't because it's a function. We have to pass the vertical line test. So if I were to take out all of the clutter from the picture, the clutter was basically just to help construct the graph. So we can see here is our cosecant function constructed in a similar manner there. The graph, once that clutter is removed, looks, well, they don't, here's one. They have it there in the graphing calculator window. Okay? So does everybody understand how the cosecant function is constructed? Okay? If you know the graph of the sine function, the features of the graph of the cosecant function follow from them. Okay? So let's do some characteristics of the cosecant function. So what about x-intercepts? There are none. None. The reason for that is because the absolute value of the cosecant function is always greater than or equal to 1, so the cosecant function would never be 0, right? You can see there are clearly no x-intercepts there. What else? Extrema. So extrema is the collective term for both maximums and minimums. They're called extrema collectively. So they are going to occur at odd multiples of pi over 2. X equals 2k plus 1 pi over 2, where k is an integer. So that is to say, I'm going to have an extremum at pi over 2, which is a max, then a min at 3 pi over 2, a max at 5 pi over 2, so they're going to alternate max, min, like that. I have a max at negative 3 pi over 2, a max at a min at negative pi, a min of the cosecant function at negative 3 pi over 2, a max at negative pi over 2, a min at pi over 2, a max at 3 pi over 2. Okay? These are local mins and maxes, not global, clearly. And so I could say that the mins will occur at x equals 4k plus 1 pi over 2, okay? So 1 pi over 2, 5 pi over 2, etc. And then the maxes will occur at x equals 4k plus 3 pi over 2, okay? Where k is an integer. And then let's describe our vertical asymptotes, where they would occur, and our period. So the vertical asymptotes will be the same as the zeros of the sine function. So where will they occur? X equals, so where are the zeros of the sine function? Integer multiples of pi. So I'll just say x equals k pi, where k is an integer. I'm not going to write k as an integer, but let's just say that that's the case throughout here. And the period of the sine function is 2 pi, so the period of its reciprocal would also be 2 pi. Okay? And you can see I have an upward U and a downward U. Those two together give me 1 period. Then an upward U and a downward U. Those two together make 1 period. Okay? So I'm going to repeat that alternating upward-downward pattern every 2 pi units, right? So the period minus 2 pi to 0, I have an up U and a down U. And then minus 0 to 2 pi, I have another up U, down U combination. So the period of the cosecant function is going to be that of the sine, which is 2 pi. Okay? I'll just mention the more general case functions of this form. So in general, or generally, more generally, so I have y equals a cosecant omega x plus b. Then I'm going to have a determines vertical stretch and compression. If a is greater than 0. In addition, reflection over the x-axis. If a is less than 0. So then we also have our omega. So I know that my period is going to be t which is going to be determined the same way as with sine or cosine, is 2 pi over the absolute value of omega. Of course, we could always write the function definition so that omega is positive by using the fact that cosecant is odd, and that can factor out a minus sign from the input. Okay? And then B is going to be my vertical translation, vertical shift. Okay? So any questions about that? Make sense? Okay, we have about 5 minutes or so, and since we have 5 minutes, I'd like to just get started on 6.6. I'll let you know your quest for Tuesday is going to be 6.4, 6.5, okay? And their part or all of that quest may be without a calculator. So there will be, at least part of the quest will be no calculator allowed. So part or all will be no calculator.
What about a scientific calculator?
Even a scientific calculator, you know, because we're dealing with stuff like, you know, graphing, things like that, we should be able to find exact values when needed without a scientific calculator, just from memory. Okay? Probably should have even had a no calculator part on the last quest, but whatever, it's fine. So let's just get started on 6.6 so that we can have a starting point for next week. So section 6.6 is about sinusoidal regression or curve fitting. And we're going to also talk about horizontal shifts of sinusoidal graphs. Those are a bit confusing, to say the least. So 6.6. Phase shift and sinusoidal regression. So let's begin with graphs of the following form. Y equals A sine of omega x minus phi plus b. So this little squiggly here is a Greek letter. The Greek letter combination in English would be ph, foot. So it's pronounced phi or phi, okay? So okay? So that's going to denote what's called or it will be related to what's called our phase shift or horizontal shift. For some reason, when you have sinusoidal functions, horizontal shifts are suddenly called phase shifts. I don't know why that is, but that's what they call them. It may have something to do with physics. So to begin with this, we're going to factor out omega from the inside, okay? And that will help us determine what our horizontal shift or our phase shift is going to be. So we have y equals a sine of omega times the quantity x minus phi over omega. Okay? So all I did, plus b. So all I did was factor out omega to get to there. So the purpose of that is once it's written in this form, we have our horizontal shift shown here as this term phi over omega, okay? So if that's positive, we're going to have a rightward shift by that amount if it's x minus phi over omega, or a leftward shift by that amount if it's x plus phi over omega. So let's just talk a little bit about our period. So the argument omega x minus phi would vary between 0 and 2 pi for a period, for a full period, right? So I'm going to have 0 is less than or equal to omega x minus phi is less than or equal to 2 pi. So my input would vary between 0 and 2 pi. My input in my sine is omega x minus phi. That would vary between 0 and 2 pi for one full period, right? So if I solve this inequality for x, I'm going to get the following. we'll get phi over omega is less than or equal to x is less than or equal to phi over omega plus 2 pi over omega. Okay? So all I did was I added omega to all three sides and divided all three sides by, excuse me, I added phi rather to all three sides and divided all three sides by omega to get this result. So basically what this tells us here is the starting point and ending point of one cycle. Now depending on where we start our cycle, usually with a sine function we started at a midline point. So that's going to give us the distance between two successive midline points, or two successive crests, or two successive troughs. Okay, that's the length of one period. So why don't we stop there, since I'm about out of time, and we'll leave it at that. We'll pick up on when we reconvene on Monday. Okay, all you people have a great weekend, and I will see you Monday.